Okay. So thank you for coming back. And we're at the second hour of our time. So we will continue.
Yeah. Okay. Yeah. So as I said in the last just before the break, the main problem that we face is the computational demand of computing the independent particle polarizability, and that scales in this particular formulation. So if we would evaluate it from this expression that was derived by Adler and Weiser, we end up with a scaling of n to the power 4 in system size, which is pretty horrible. But one can reduce the scaling, at least in this case. It's described in this particular paper by a colleague of mine, Mersu Kaltak and Kiri Klimesh, who was a postdoc at our institute at the time. And by Georg Kresse, we can reduce that by 1 order of magnitude to cubic scaling. That sounds pretty bad already, cubic scaling, but let's not forget that the worst scaling steps in density functional theory in most plane wave codes, I would say all plane wave codes, is cubic as well. So the orthonormalization of the orbitals scales cubically as well, with a pretty different p-factor than for RPA, I must say, but still, underlying scaling is cubic. So how do we end up with the cubic scaling algorithm for the random phase approximation? Well, we start with the Green's function and express it in imaginary time. That is shown here. And so what do we recognize here? We recognize, again, 1 electron orbitals and energies, as before. Those are the ingredients. And the sum over states, over all states. And that gives us a Green's function, which is in R and R prime. So storage of this is expensive, and that scales quadratically with system size. R and R prime. And the polarizability, as I mentioned before, can be written and can be evaluated as a product of Green's functions. And we see here that it's a point-by-point product in R and R prime. So this is, so in the formulation of Adler and Weiser, that would getting this would scale with n to the power 4, and what we have here scales with n to the power 2. So our most expensive step becomes much less expensive in terms of scaling with respect to system size. So we follow this by a cosine transform from imaginary time to imaginary frequency, and then we can evaluate our ACFTT correlation energy, our RPA correlation energy, as we saw before from independent particle polarizability at these frequencies and the Coulomb kernel, the bare Coulomb kernel. So this scales in total. The worst scaling step in this is in fact the evaluation of the logarithm. Because to do that, we need to diagonalize a large matrix, and diagonalization scales cubically. So this is this is, if you so want, is the worst scaling step. And before, the worst scaling step was the computation of the independent particle polarizability, but that now scales quadratically in system size. So as I said, the storage of the Green's function, and now we need to store this, that is expensive, and it scales cubically in system size. And we need to do that for a set of times tau, or a corresponding set of frequencies, omega. And what we need to reduce our storage demand is sets of cleverly chosen times and frequencies. These, by the way, do not, these times and frequencies, they do not scale with system size. So they are independent of our system. So what we need is as small as possible sets of times t and frequencies. And that is where the work of Kartak came in. So what we want to do, so the general problem is that we want to represent a particular function in a basis of n functions that depend on two parameters, the parameter alpha and beta, and we want to approximate this particular function by such a quadrature, if you want, where the set I is as small as possible. So we do that in the so-called minimax sense. That is, so what we seek is a set of parameters alpha and beta for a number of functions n, where n we would like to have as small as possible in such a way that the maximum error is minimized over a certain interval for x. So that is the general problem that we try to solve. And that particular solution is called the minimax solution. So the minimax fit to a particular function is defined in that way. So how do we use that to determine time and frequency grids? Well, let's start out with a frequency grid. So here we have, try to find my notes. So the optimal frequency grid to represent the polarizability we seek in the following manner. First, we realize what the functional form of the polarizability is in general. So that is written here, and where x is essentially an energy difference. So let's say energy difference between an unoccupied and an occupied state, and this phi you see here, those are these products of orbitals. So our polarizability has this general functional form, and the frequency and energy dependence of it is given here. So what we now seek is a frequency grid and weights that basically give the best fit to a particular component of the MP2 energy, and that is written here. In terms of this polarizability, there's a part of the MP2, the Miller-Placid energy, that is called the direct part of it, that can be written in this form. And we seek a grid of frequencies and quadrature weights that gives the best fit to this particular correlation energy within the basis of these functions, and that is in the minimax sense. So in the minimax sense, the problem takes this particular mathematical form. So 1 over x is approximated by these functions to the power 2, and we seek a set of frequencies and weights that minimize the maximal error that is made over a range of eigenenergies. So basically, you take your highest occupied state, your lowest occupied state, and your highest unoccupied state. This gives you an energy range, and over that range, you take this minimax fit. So in the end, what you get, so if this is the exact expression for this direct Miller-Placid 2 energy, then we get an approximation to this energy, basically by evaluating this at a certain number of frequencies and multiplying with this quadrature weights. And from this approximation, we then know that the maximum error made on this interval of energy is minimized. So, and one can compute that maximum error and then decide, for instance, what you start out with is saying, I take, for instance, 8 points or 12 points or 16 points, and then you compute and you minimize the maximum error, and then you decide whether you're satisfied with this maximum error on this energy interval. Otherwise, you need to increase the number of points you take. So the same thing can be done for the time grid, separate problem, but completely analogous. So you have the same functional form, but now in the time, the same function, but now of a different form, because we have transferred it into the time domain. And the same thing we do for this Malaplicit, direct Malaplicit 2 energy. And we make a minimax fit again for a number of time points. And basically you get again an approximation to this energy by taking a certain set of time points and a certain set and corresponding weights to it. So the only thing that is still missing is a transform between the two. Normally, if you would, here we have this, we have the independent particle polarizability in the frequency domain, imaginary frequencies, imaginary times, and between them there's normally a cosine transform, as I showed you as a step in our algorithm where we need to do this cosine transform. But now we have this non-uniform frequency grids and non-uniform time grids. And we need to establish a non-uniform cosine transform, something like that, between the two that takes this particular form. And what we now will seek is these weights in this transformation. So this is a matrix K and L that connects our frequency points to our time points in the other direction, if you so want. And we seek an optimal transformation between the two, again, by solving a minimax problem. So we have a frequency grid and we have a time grid, and we have a transformation between the two. And typically these sets of frequency and time points can be chosen to be fairly small, and that is shown here. So this is the energy. So look, let me see, absolute error in energy for zinc oxide and silicon. So here we basically compute the correlation energy in the random phase approximation for zinc oxide and silicon with both algorithms, with the n to the power 4 scaling one and with the cubic scaling one. So the blue dots are the n to the power 4 RPA calculations, where we take fairly large frequency grids because there's a frequency integration there as well. But it's a completely standard one. And these pink dots, they are the cubic scaling RPA energies, where we use these minimax grids and this non-uniform cosine transform to go from the minimax frequency and between the minimax frequency and time grids. And what we see here is that already at something like something between 8 and 12 points, we are already at an error in the energy that is of the order of a micro EV. So this is where, so there's really no need to go to large grids. And where in our old GW algorithm, if you so want, we would use, I think, something between 50 and 100 frequency points. Here we can essentially limit ourselves to something like 8 to 10 points in these grids. and which is pretty essential because of the storage demands. So we need to store our Green's function, for instance. We need to store for all these time points. So for 8 or 10 time points. And after this transition, and the same thing holds for the independent particle polarizability. We need to store this for a bunch of time points, and the storage of that scales quadratically with system size. But the good news is that that something like here, so this is a system of something like 200 to 300 atoms can be done on someone, I think Georg mentioned 200 cores, seems to be a bit of a strange number. So I think it's of the order of several hundred compute cores in about an hour. So and that is really a lot better than what one could do with this n to the power 4 scaling. Okay, yeah, basically I then have only a few slides that should convince you that the scaling is actually as I say it is. But let me skip those. Maybe mention a few people, well, especially Martijn, who came up with these optimized grids, and has done quite a nice work on finite temperature grids. So, for instance, if you want to do this for metallic systems, you can do that now because of his nice work. I've put the papers here. You can, if you're interested in this kind of things, you can look at them at your leisure. One thing I would like to mention is that within the RPA, we also have expressions to evaluate forces. So there's a generalized, there's a generalization of the Hellman-Feynman forces that is valid for this random phase approximation, total energies. So we have forces and stress and total energies, if you so want. It's expensive. So be warned, it's really expensive. But because we have this whole range of properties from the RPA, there's nice things one can do in terms of machine learning. And that is actually the topic of the next presentation. So let's move to that. Yeah. Okay. So let me kill this and then. No, that is wrong. Yes, it. Maybe. Well, I think I might know. I think it chooses the wrong screen. Yeah, but I move it to this side and then.
Option.
Yeah.
Yes.
Does that work? No. Okay. Okay. Swap.
Okay.
Yeah, let's move to the beginning.
I think we need to show.
Yeah.
Show. The Zoom is.
Maybe if you go on the presentation. You need to swap again, I guess. But this is annoying.
Maybe changing something. Was this here before?
No, it was
No.
all in the.
Which shows the
Do you know how to get the zoom toolbar to appear? Zoom bar to. Do you know how to get the zoom toolbar to appear? Ah, there it is. Yes. Yeah, yeah. Oh.
done.
Yes.
Good.
How did you do that? Okay, thanks. Okay. Yes, so for machine learning, we have basically three ingredients. We have we need a database of reference calculations, and that is maybe the only thing that is VASP specific in this whole presentation, if you so want. So we are definitely not the inventors of machine learning. So the thing that, well, at least it was special when we started doing it, is the way we create a database of reference calculations by on-the-fly training. But so the first ingredient is this database of reference results that you need. And then you need, in the case of these machine learned force fields, at least, you need some representation of a local environment. So I need to be somehow able to say the environment of my atom so-and-so looks like this and that. So I need to describe this in some way, a descriptor or a fingerprint. Many terms have been coined there. And then I need, as a third ingredient, I need some algorithm that learns my reference results in terms of these descriptors. So that is essentially what is shown. Now it's at least doing something. Yes, okay, good. Good, yeah, and that is what is shown here. And so a database of reference calculations, then some way of saying, well, where am I? To describe my environment, and then some fit of this particular of these reference results in terms of these environments. So the key assumption that we make is that we can describe our potential energy as the sum of atomic energies. And so if I have n atoms in my structure, then my total energy is a sum over some energies per atom. And there's no physical justification that tells me that I can do this. So this is an assumption that we can do this. It will turn out for some applications, it will turn out to be a very useful assumption. There are some, for instance, I think it's Kubo-Greenwood transport theory is formulated in terms of local energies. And normally you don't get such a thing, but from machine learning you would get it by making this assumption. And so atomic energies are contributions, are functions of the local environment. That is the second assumption that we make, and that is sort of described here. We have a boron nitrate, and we have a boron and a nitrogen, and they have a local environment. So we have some cutoff radius around an atom that defines its local environment, and this local energy is a function of whatever is present in this local environment. Now, we cannot simply express the local environment in terms of the Cartesian coordinates of the surrounding atoms. Well, we could do that, but it would not be very efficient. We would like something that is rotationally invariant. And so if we would do that, we would get an express. So if we would simply use the coordinates of the atoms around it as a description of the local environment, we would have something that is translationally invariant, but not rotationally. So we seek a descriptor that has both of these invariances, translational and rotational. So there's many ideas how to do that. So Baylor and Farinello pretty much pioneered something called symmetry functions, and there's a lot of work by Kawachani, and there are many other ideas how to characterize a local environment. But the basic idea is that we expand a broadened density distribution of atoms around a central atom into spherical harmonics and some other function. Well, in this case, see here spherical harmonics and Bessel functions, radial Bessel functions. And when I say density distribution, this does not mean electronic density, right? So now we are talking about ions, but we broaden them with Gaussians, so we get a density distribution of atoms. Otherwise, we would have a set of delta peaks. It's more difficult to expand. We broaden that with Gaussians, and then we basically expand it in spherical harmonics and Bessel functions. And you get a bunch of coefficients for that. So this particular expansion would be invariant under translations, but not invariant with respect to rotations. So that cannot be the descriptor of choice. We said we want both of these invariances, but we can construct suitable quantities out of this particular expansion by taking the pair correlation function. So we'll use a function that basically depends on, basically tells us how many atoms around atom I, how many other atoms there are at a certain distance r. And that is obviously, that particular thing is obviously rotationally invariant. And an angular correlation function. And that tells us how likely is it to find, if this is our central atom, atom I, how likely is it to find another atom at a distance r, and atom J at a distance r, and another one, K at a distance S with an angle of theta between them. So, and of course, these quantities are invariant both under translation as well as rotation. And the nice thing is that that we can deduce them out of this particular expansion. So if we make this expansion of the local environment around an atom within a certain radius of this broadened ionic density, then we can get the pair correlation function and this angular correlation function from these expansion coefficients. And so these were the expansion coefficients in this original function that I showed you with the spherical harmonics and the Bessel functions. So these are the coefficients of our pair distribution function, and this is the angular distribution function where we have another set of coefficients, but computed out of the same set. Yeah, so then of course there's some choices to make, because we have here I said we do an expansion, so we do an expansion in a certain set of Bessel functions and a certain number of spherical harmonics. So there are some choices to be made there. Mostly we take something like 8 Bessel functions or so, and go up to L to L quantum number of 4 in the angular expansion. And that means that we end up for a single, typically for a single atomic system with a single atomic species, we end up with something like a few hundred coefficients. So these coefficients that we store that basically describe our local environment, and as per atom, if you have only one species, there's a few hundred of these coefficients to be stored. As soon as you have a multi-component system and more than one atomic species, then this goes up quite a bit. We end up with several thousand of these coefficients per atom that describe its environment. Yeah? So that would be the total length of the descriptor, if you so want, for a certain atom would contain several thousand coefficients. So this was our total energy, right? The sum of these local energies. We have not specified any form for that yet. And from that, we can also derive forces. And so we can take the derivative of this total energy with respect to the position of an atom in a certain structure. So atom J in structure A, if you so want, and go through the chain rule, we can, from this expression of the total energy, we can get forces, we can get stresses. Of course, we have not said what the actual form of these local energies would be. So what would be a suitable form to assume for that? Let's go to the amount of data that we'll be collecting, if you so want. So typically, if we train with this on-the-fly training, what we would end up with would be something like 500 structures, typically, something like that, for instance, with well, let's say several hundred or 100 atoms per structure. So what we would have in terms of training data would be, well, we have 500 structures, we have 500 total energies. With 3 force components per atom and 100 atoms and 500 structures, we have something like 150,000 data points for the forces. And for the stress, we have 6 stresses per structure, something like 3,000. Yeah? And the number of descriptors for each atom, and like I said, we could characterize the local environment with something like 1,000 coefficients to be stored. And we need to create a nonlinear function. This is U, and there's no reason to assume that it's linear. A nonlinear function of these descriptors to fit this available data. Now, there's a few routes that were taken. One very important and very convenient one is to go through neural networks. And you say, so when you don't specify any function form, but basically you have the descriptors on one side of your network and your energies on the other side, and you adapt all these weights until those match. That is not the thing that we do. And so we are faced with the problem that if we want to make such an expansion in a nonlinear expansion, but essentially you could ask yourself, what is the size of that problem? So for a complete set of functions in these coefficients, let's say in 2D, where we have only two functions, x and y, then a complete set would be x and y, x squared, x, y squared, and so on and so forth. There's really no reason where to stop. So essentially that means that if we have 1,000 descriptors per atom, that we're seeking for an expansion of something, a complete expansion in 1,000 dimensions, which is of course out of the question, completely intractable to do. So, and that is where this other route, so of course the neural networks, they circumvent this problem. They don't go through this reasoning at all. We do, but to circumvent the problem of having to go to some complete set or complete enough set in a 1,000-dimensional search space, we apply the so-called kernel trick. It's also not invented by us, but described first, I think, by, what is it, Hoffman, Schurkopf, and Schmoyan. The link is here, or the reference. Anyway, so the trick, the kernel trick is that you introduce so-called similarity kernel. And if I want to know the local energy around my atom, so I have a descriptive vector of a certain atom, and I want to know its local energy, then I evaluate this similarity kernel. So I measure the similarity between my local environment in question and a set of reference local environments. And this kernel function can in fact be freely chosen. It just should be a function that basically, if I have a local surrounding around an atom and it's very similar to a reference that I have, then this function should be close to 1. And if it's completely dissimilar to the reference local environments that I have collected, then this function should be 0. That is essentially the only thing that it needs to do. So we will expand these local energies in terms of this similarity, of these similarities and associated weights. And those are the regression coefficients that we have to determine. And basically, we can train any nonlinear functional dependence with this method. So to have a look at, let's say, a pictorial representation of this procedure, let's assume that our similarity kernel is a Gaussian. So I have some vector of descriptors, and basically I have a distance between a reference that I have stored, reference result, and my local environment of consideration. And so if they're very similar, then this is 0, and this will simply amount to 1. And if this is somehow large, then this will go to 0. So let's say we have an unknown observable function, and we have only one coordinate here, and we have 1, 2, 3, 4, 5 reference descriptors. Yeah. So x5 or x1 to x5. Then we put the Gaussian on each of these points, obviously. Those are these kernels. And then we adjust the weights in some way that we'll come to. These are these 3 factors here. And now for any point in between these reference points that we have some functional form. That is some approximation to the true functional form, right? This minty line is the true functional form. We have few data points, and this particular expression will evaluate to this blue line. So that would be our fit to the unknown observable function. So how good this fit is, of course we do not know. But as we collect more reference points, it should become better and better. So to wrap that up so far, our total energy is the sum of atomic energies, and they are these atomic energies are sums of weighted kernels, these weighted similarity kernels. And so this was our Na is the number of atoms in a certain structure A, and basically we need to evaluate. So if we have an atom I in structure A, then its energy contribution to the total energy is found as a sum over these reference configurations, evaluate the similarity between these configurations and the actual environment of our atom I, and determine these weights somehow, and that is the learning stage, and that gives us then energy. And the same thing goes for the forces, right? So the forces derive from exactly the same information, basically weights and these reference configurations. So, and this similarity kernel measures the similarity of the environment of any atom and the local reference environments that we have collected and stored. And I'll come to that. So the descriptor describes the local environment of an atom up to a certain radius around it, and it contains expansion coefficients of the pair and angular correlation functions. And these are invariant with respect to translations and rotations. So what do we now need? And we need a database of training structures, and it's ionic positions and lattice shapes and forms. And for these training structures, what do we need? We need to know the energy of these structures and the forces and the stresses on the cells. And the other thing that we need is a set of these local reference configurations. So we need to store a number of descriptors for typical configurations around atoms. And it makes sense to take these configurations out of this training set. So we extract these reference configurations out of this training database. But how do we do that, and how many should we take, and so on and so forth? And how can we arrive at a suitable database of structures to train against? So the idea that we use is to do this on the fly. So basically, we create our training database on the fly during a molecular dynamics run. So we start to do molecular dynamics on a structure, and basically at each step, and let's assume that we already have a bit of training under our belt. So we have already arrived at a rough model of our that describes our forces and energies. So what we now do during this MD is we evaluate the total energy and the forces predicted from our model. And then we need to decide whether this prediction is good enough. And for that, we use Bayesian regression. So not only can we get a prediction, but we can also get a prediction of how good our prediction is. So essentially that we use. So we get the prediction of our energies and forces and of the uncertainty in those from our model. And then we simply ask, well, is this good enough, this prediction? If it's not, then we need to do a first principles calculation for this particular structure. Yeah? So within this MD. And from this first principle calculation, we then select reference configurations. So basically, we look at the atoms where the prediction in the forces was the worst, above a certain threshold, and those we will add to our reference configurations. And the structure for which we have performed this ab initio calculation is added to the set of training structures. So our set of reference configuration grows this way, and our set of training structures grows this way during an MD. So if we would get a satisfactory result in terms of the Bayesian error from our current machine learned force field model, then we'll skip the ab initio step. We'll do a classical molecular dynamics step, based on that prediction and move on. Yeah. So ideally, at some point, of course, you would be doing only these classical MD steps at some point. As your set of training structures has grown to a certain point and your set of local reference configurations is suitable, you would not be doing any ab initio steps anymore. And the ratio between that for an MD is pretty nice. So we see that, that typically during a training MD run, you do ab initio steps maybe 1 or 2% of the time. So in the end, so if you do 10,000 steps, only 1 or 2% of those would be ab initio calculations. And of course, once you have then arrived at the suitable force field, you could skip up doing ab initio completely. Say, okay, I only want to evaluate the force field anymore. That would be the general idea. Yeah. So let's say the key ingredient there is, of course, that one can use this Bayesian variance to judge whether you can trust your current model or not, right? That is the idea behind that. And what is also nice is that one can combine this so one could, for instance, take phase A of a certain material, train for it, take the force field, restart the training for another phase of the same material, and improve your force field so that it can describe both. Those are the things that one would like. Or what we often do is do this in an MD, but during a heating run. So start at a lower temperature and then increase the temperature and get more variation in your local configurations. Maybe even melt the structure up to amorphous. So this would be an example of that, for instance. Solid silicon heated from, so this is not up to melting, but heated from 0K to 800K. And what one sees here is, this is the average fitting error. And these are the Bayesian errors that you see here. Yeah, so this is pretty typical. That you get the Bayesian error estimation underestimates the actual error. Bayesian error can only tell you what is the expected error within my model, but it cannot judge how good your model is, right? So, yeah. So, yeah, that is very typical. So this is the threshold that we set. It's a threshold that is updated during the molecular dynamics run. So it takes the average of the last 10 Bayesian errors that were below it as a threshold. So, and as you jump over the threshold, an MD step would occur, right? And what we aim for instance, but that will of course depend on what you plan to do with the force field afterwards. But very typically, we would like the final errors, the root mean square errors, to be below something like a few millieV per atom, and the errors in the forces below 100 millieV per angstrom, something like that. That would already be a fairly good force field. But of course, if you would want to do phonon calculations with that, then you would need more accurate forces. So it will depend on what one plans to do with it. So yeah, like I said, the Bayesian variance is usually lower than the average fitting error, but it still remains a good estimator. So that is why we can use it. So now we come to, so what did we now discuss? Basically, we had selection of training structures and selection of local environments, but not how we then actually train. So the training is solving a least square problem. for these weights, for these quadrature weights, by which we multiply the similarity kernels. So the vector epsilon collects all the data that we train against, so all energies and forces and stresses for all the training structures. And this large phi here is what we call the design matrix, and that collects all linear relations for each structure, essentially this particular similarity, this sum of similarity kernels that gives us the energy. And of course, we have this for the forces, we have similarity, well, derivatives of the similarity kernels. So essentially in this design matrix, the rows of it, and we have rows that are connected with the energies that we have collected, basically contain this sum over atoms in a structure and then the similarities and so. And then we have rows that contain associated information for the forces. So if you look at the dimensions of this matrix, then we have a number of rows. What did we say? We had something like 500 energy, 500 energies. If we have 500 training structures, we have 500 energies. If we have 100 atoms, then we have for 3 components per force, we have these 150,000 rows associated with the forces, and we have 3,000 rows associated with the stresses. And the columns in this design matrix go over all chosen reference atoms. So let's assume that this is 500. Then we have a design matrix that is something like 150,000 by 500. Yeah. So we have something like 150,000 rows, and we have 500 columns, and we are solving that against 500 weights. So we have something of the order of 150,000 equations and 500 unknowns. So it's a massively overdetermined problem. So the solution to this is by solving the so-called normal equation. So we multiply phi by its transpose from the left, and then we end up with this thing here, which is the so-called normal equation. And so if we had this was something 150,000 by 500, well, if we do this operation, then we are at a rectangular matrix, at a square matrix, 500 by 500. And that to get the weights, one should then, for instance, invert that and arrive at the weights. And that is then essentially our training step. We have 500 of these chosen reference configurations, and we have the weights by which we multiply the similarity kernel state. So that is essentially the force field, these weights. Now the problem is that many times this matrix here has eigenvalues that are very close to 0. So this needs to be regularized, and the regularization is done by adding something on the diagonal. And this an optimal regularization can be done essentially. So these parameters here, the sigma v and sigma w, can be inferred from the, well, what is it called? Let me quickly look that up. Basically, it follows from the Bayesian error estimate that we have, and it is called the from the so-called evidence approximation. Yes. So we have a model that will predict how we should regularize this normal equation. Remaining problem is that when we would regularize it optimally, that often the condition number of the resulting matrix can be really horrible and approach machine precision. So that is sort of the remaining problem, that we cannot always optimally regularize that particular equation. So there is a way around that, and that is by solving using the so-called pseudo-inverse that you can obtain from a singular value decomposition of the design matrix. And that would be this thing here. So it's not an actual inverse because this is not a square matrix. But from a singular value decomposition, we can get a pseudo-inverse and use that to solve this problem. But that can only be done in a post-processing step with the code. So that circumvents the problem that we would have here with this conditioning. And we end up at a slightly more accurate force field than when you solve the normal equation. But when we do this on-the-fly training, we need to stay within this Bayesian regression model. We need to go this route. At the end, we can retrain a single step using this pseudo-inverse and get a slightly better force field that way. So, how am I set for time? Yeah. Okay. Then I will leave. The description of the files for you to peruse at your leisure. I propose that for the hands-on training, that if you're interested, at least that you focus on this machine learned force field tutorial that we have. I will put up. Can I put up a slide as well on the board in the Yeah. Okay. Then I will put up a slide. So we have a machine set up in the cloud where you can log on to. I have created some login accounts for you, and there's an environment where one can run the tutorials. So there's a whole bunch of tutorials that we commonly offer. In this case, there's also one for machine learned force fields. So if you'd like, you could run that maybe in the afternoon.
According to the program, we should go to the whole next. Now around 45 minutes, I think, lunch break, and then at 12:15, jump.
Hi, Marcus.